Quarks form every proton and neutron, yet no experiment has ever produced a free quark. Each time laboratories attempt to separate them, the strong interaction described by quantum chromodynamics behaves in a precise and repeatable way. The force does not fade with distance. Energy accumulates in the gluon field between the quarks until it becomes energetically favorable to create new quark-antiquark pairs. Instead of isolation, detectors register the appearance of additional particles. This pattern is grounded in calculation and measurement within the Standard Model, confirmed across decades of high-energy experiments. Deep inelastic scattering at SLAC in the late 1960s first revealed substructure inside the proton, exposing point-like constituents later identified as quarks and gluons. Experiments at CERN extended this picture to far higher energies, yet quarks continued to appear point-like down to the smallest distances reached. Modern detectors capture their presence indirectly. Sprays of particles known as jets trace the momentum and color flow expected from quarks, even though no single quark ever arrives alone. The same interactions account for why most of the mass of ordinary matter arises from QCD binding energy, while the Higgs field contributes only a small fraction. All of these observations point to a persistent limit that appears whenever matter is examined at its most fundamental level. Part 1. If quarks build everything, why does nature refuse to show you even one? At some point, repeated experiments stop feeling like coincidence. Across different machines, different energies, and different decades, attempts to isolate quarks always trigger the same physical response. Separation never completes. Instead, detectors register the appearance of new particles, produced in a way that follows calculation rather than chance. This consistency forces a shift in perspective. The absence of isolated quarks is not a gap in experimental reach, but a result that emerges directly from how the strong interaction operates. What experiments encounter is not failure, but a boundary enforced by the dynamics of quantum chromodynamics itself. That response has been confirmed in fixed target experiments, collider data, lattice simulations, and searches extending beyond Earth itself. What emerges is not an absence of quarks, but a boundary enforced by the strong interaction, one that defines how matter can exist at all. This story begins where modern particle physics truly changed direction, in the late 1960s, at the Stanford Linear Accelerator Center. At that time, protons were still often described as compact objects with internal softness, something like a charged cloud. To test this picture, researchers accelerated electrons to extremely high energies and aimed them directly at hydrogen targets. These electrons probed distances smaller than 1 femtometer, about 1/4,000,000th of a meter. The detectors did not show smooth deflections. They showed sharp, abrupt scatterings, the kind expected when a projectile strikes something small and stiff. James Bjorken worked through the mathematics. Richard Feynman worked through the physical interpretation. The proton behaved as if it were built from smaller entities, each carrying momentum independently. Feynman called them partons. Within a few years, those partons were identified with quarks, the entities Murray Gell-Mann had proposed earlier in 1964 to organize the rapidly growing list of hadrons. What began as a bookkeeping tool became something far more concrete. Matter had an interior, after all. But this interior came with rules no one expected. As experiments improved, quarks continued to appear in scattering data, yet they never appeared as individual particles. Each measurement sharpened the paradox rather than resolving it. The more clearly quarks were detected indirectly, the more firmly they refused to stand alone. The explanation arrived through a new theory, quantum chromodynamics, usually shortened to QCD. QCD describes how quarks interact using particles called gluons. Both quarks and gluons carry a property known as color charge. This color charge has nothing to do with light or vision. It exists to make the mathematics work and to match experimental data. There are 3 types of color charge. Observable particles must always combine in ways that cancel color entirely. A proton achieves this by combining 3 quarks, each carrying a different color. Mesons achieve it by pairing a quark with an antiquark. No confirmed particle violates this rule. At first, this requirement seemed strict but manageable. The deeper surprise lay in how the strong interaction behaves when quarks are pulled apart. In gravity and electricity, forces weaken with distance. In QCD, distance has the opposite effect. When two quarks begin to separate, the gluon field between them does not thin out, it tightens. Energy accumulates in a narrow region connecting them, often described in calculations as a tube of field energy. Lattice QCD simulations show that this tube stores roughly 1 giga-electron-volt of energy per femtometer. That number carries a consequence that no experimental design can avoid. When enough energy accumulates, the field converts into matter. A new quark and antiquark appear, splitting the tube into two shorter ones. Instead of one isolated quark, the result is two composite particles. This outcome does not depend on timing or precision. It follows directly from how the strong interaction is built. Tool harder, and the system responds by creating more structure, not by allowing separation. Nature does not block the attempt, it redirects it. Throughout the 1970s, physicists tested this behavior from every angle they could imagine. They searched for particles with fractional electric charge, a clear signal of free quarks. None were found. They examined materials exposed to cosmic radiation for billions of years. Still nothing. One particularly careful effort involved lunar soil returned by NASA's Apollo missions. The Moon lacks the atmospheric and magnetic shielding of Earth. If free quarks existed naturally, some might have lodged there over immense spans of time. Extensive measurements found no trace of them. Meanwhile, accelerators pushed to higher energies. Detectors became more precise. At CERN, proton collisions produced enormous sprays of particles. The patterns were unmistakable. Quarks were present at the start of each collision, yet only hadrons reached the detectors. Physicists learned to read these events through jets, narrow cones of particles whose energies and directions preserved the motion of the original quarks and gluons. The agreement between QCD predictions and jet data became one of the most accurate successes in modern physics. Still, no quark ever arrived by itself. By the early 1970s, theory caught up with observation. In 1973, David Gross, Frank Wilczek, and David Politzer discovered a property of QCD, now known as asymptotic freedom. Their calculations showed that at extremely short distances, the strong interaction weakens. Quarks behave almost independently, but only while confined inside a hadron. At larger distances, the interaction strengthens. The same equations explain both behaviors without contradiction. This result earned a Nobel Prize because it unified decades of puzzling data into a single framework. It also removed the idea that confinement might disappear with enough energy. Later, lattice QCD confirmed this picture numerically. By placing quarks and gluons on a discretized spacetime grid and solving the equations on supercomputers, physicists showed that confinement emerges automatically from the theory. No additional rule is required. This realization quietly reshaped how mass itself is understood. Quarks have very small intrinsic masses. An up quark weighs only a few mega-electron volts. A proton weighs about 938 mega-electron volts. The difference comes from energy stored in motion and fields governed by QCD. Most of your mass is not located in particles sitting still. It is energy locked into stable arrangements by the strong interaction. This conclusion is supported far beyond laboratories. Observations by NASA and ESA show that ordinary matter accounts for only about 5% of the universe's total energy content. Even within that small portion, QCD dominates what mass means. Galaxies shine because of energy organized at the quark level. Inside a proton, nothing remains fixed. Deep, inelastic scattering reveals a dense environment filled with gluons and short-lived quark-antiquark pairs. Pattern distribution functions, refined over decades, show that the three valence quarks carry only part of the proton's momentum. The rest belongs to the gluon field itself. This makes isolation a misplaced expectation. A quark is not a bead embedded inside matter. It is a role within a system that reorganizes instantly when disturbed. Remove the role, and the system rewrites itself. Murray Gell-Mann later noted that quarks began as a useful classification and ended as real entities with strict limitations. The name stayed, the boundaries stayed, physics adapted around them. Prediction continued to improve, even as intuition lagged behind. Richard Feynman once remarked that nobody truly understands quantum mechanics. He was not rejecting its accuracy. He was pointing to the distance between calculation and everyday reasoning. Confinement lives precisely in that distance. Every modern test supports the same picture: high-energy collisions, numerical simulations, searches across Earth and beyond. All agree. Quarks define matter without permitting isolation. This is not a limitation of observation. It is a condition of existence at that scale. When isolation fails at every scale tested, experiments are forced to confront a different limit. Measurements no longer ask how quarks separate, but how they behave when probed at distances where size itself has not appeared. In high-energy collisions, quarks respond as entities without measurable extent, leaving detectors to record interactions, momenta, and quantum numbers, yet never an internal structure. At that point, the language of inside and outside stops matching what experiments can confirm. Part 2. What are quarks made of, if every test says they have no inside? Here is a result that unsettles even experienced physicists. When matter is struck hard enough to probe its interior, the instruments never reveal a smaller object inside a quark. They reveal motion, distributions, and response patterns, but no substructure, no layers, no core. At the smallest distances we can reach, quarks behave as if they have no size at all. This conclusion did not arrive suddenly. It emerged slowly, through a sequence of experiments that forced scientists to revise their picture of what inside even means. The story begins again at Stanford, at SLAC, in the late 1960s, when electrons were accelerated to energies never used before for this purpose. At lower energies, protons had appeared soft, almost cloudy. Their charge seemed spread out, and early scattering experiments fit that image well. But as the electron energies increased, the pattern changed. Electrons scattered as if they were hitting compact targets. The higher the energy, the sharper the deflections. This told researchers something crucial. The proton was not a smooth ball. It behaved like a collection of smaller entities, each able to take a sudden blow and recoil independently. This was the birth of deep, inelastic scattering. Richard Feynman introduced the language that made sense of the data. Inside a fast-moving proton, he said, there appeared to be partons carrying fractions of the proton's momentum. The faster the proton moved, the more sharply these partons appeared. What mattered was not where they sat, but how momentum was shared. As experiments improved, the partons revealed themselves as quarks and gluons, exactly as quantum chromodynamics predicted. But something unexpected remained. No matter how high the energy, no matter how fine the resolution, the scattering results never showed any hint that quarks themselves had internal structure. They behaved as point-like objects down to distances smaller than 1/10,000th the size of a proton. In ordinary units, that means smaller than 10 to the minus 19th meters. Physicists pushed further. At CERN, higher energies allowed collisions that briefly recreated conditions similar to those of the early universe. Detectors traced how quarks and gluons shared momentum before transforming into hadrons. Again, quarks acted as if they had no spatial extent. This absence of size was not an assumption. It was measured. Scattering cross-sections matched the predictions for point-like particles with extraordinary precision. If quarks had an internal structure, the data would have shown deviations. None appeared. This forced a quiet shift in language. Asking what quarks are made of began to sound less like a technical problem and more like a mismatch between everyday intuition and quantum field theory. At this scale, Particles are not miniature objects with parts, they are excitations of fields. Quantum chromodynamics describes quarks as fundamental fields. Their properties, such as mass, charge, and color, are inputs to the theory. The equations do not contain smaller components waiting to be uncovered. Every experiment so far agrees with this description. There is a historical echo here. In the early 20th century, electrons were once imagined as tiny spheres. Scattering experiments later showed that electrons too behave as point-like down to the smallest scales measured. Quarks followed the same pattern, but with an added twist. Unlike electrons, quarks can never be observed directly. Their point-like nature is inferred entirely through their influence on other particles. Jets, in particle detectors, carry their momentum. Structure functions encode their distributions. Evidence accumulates without ever delivering the object itself. The proton, once thought simple, became something far richer. Experiments revealed it as a dense, dynamic environment dominated by gluons. At high energies, gluons carry most of the proton's momentum. Quark-antiquark pairs appear and disappear continuously. The familiar picture of three quarks survives only as a statement of identity, not of composition. This realization deepened in the 1990s as pattern distribution functions were mapped with increasing accuracy. Each new dataset refined how momentum was shared at different energy scales. The proton became less like a container and more like a pattern that persists while its contents change. NASA and ESA missions, while focused on cosmic scales, reinforce the importance of this microscopic behavior. When the James Webb Space Telescope measures the mass of galaxies, it is ultimately tracing energy organized by interactions that begin at the quark level. What happens inside protons shapes what shines across billions of light years. Physicists sometimes describe quarks as point-like because that is how they respond in experiments. This does not mean they are mathematical abstractions with no physical reality. It means that at the scales we can reach, no smaller structure affects their behavior. In practice, point-like means complete. This completeness is unsettling. For centuries, progress in physics meant going deeper, finding smaller constituents beneath familiar ones. Molecules gave way to atoms. Atoms gave way to nuclei and electrons. Nuclei gave way to protons and neutrons. Quarks appear to end that sequence. Theoretical efforts have explored whether quarks themselves might be composite. Models involving hypothetical preons were proposed in the 1970s and 80s. These models predicted deviations in scattering data. No such deviations have been observed. Every increase in experimental resolution has tightened the bounds. If quarks have internal structure, it must exist at scales far beyond current reach, smaller than anything yet probed. For now, the data draw a clean line. Carl Sagan once wrote, "Somewhere, something incredible is waiting to be known." In particle physics, the incredible part is often how stubbornly simple the smallest elements appear to be. Quarks resist subdivision not by hiding, but by offering nothing more to divide. The language of fields helps clarify this. In quantum field theory, particles are not objects in space in the usual sense. They are localized excitations of underlying fields. Asking what they are made of is like asking what a wave in the ocean is made of beyond water itself. The description stops at the field. This does not mean curiosity ends, it changes direction. Instead of asking what lies inside quarks, physicists examine how quark fields interact, how symmetries shape their behavior, and how these interactions give rise to mass and stability. Understanding shifts from composition to organization. The experiments that revealed this shift were not abstract. They involved decades of work, teams of thousands, detectors the size of buildings, and calculations that pushed computers to their limits. Each result narrowed the range of possible explanations. What remains is a picture both precise and demanding. Quarks behave as fundamental, point-like entities. Their effects can be measured with extreme accuracy. Their interior offers no further layers to explore. The familiar idea of made of loses its footing here. As measurements probe deeper, another feature of the strong interaction becomes apparent. Quarks continue to behave as entities without measurable size, yet the binding between them grows tighter rather than weaker. This immediately sets the strong force apart from every other interaction tested in nature. When experiments attempt to pull quarks farther apart, the response of the force follows a rule that cannot be ignored, one embedded directly in how matter is structured at its most fundamental level. Part 3. Why does the strong force get stronger when you try to separate things? Most forces weaken as distance grows, yet the strong interaction responds in the opposite way, tightening its grip the harder separation is attempted. This single fact overturns everyday expectations and places the strong force in a category entirely its own. To see why this happens, it helps to begin with comparison. Gravity fades as objects move apart. Electricity does the same. Even magnetism relaxes with distance. These forces spread outward, thinning as space opens between sources. The strong interaction does not spread. It concentrates. The reason lies in how quarks carry color charge and how gluons respond to it. In quantum chromodynamics, color is not a label but an active property. Quarks carry color. Gluons carry color as well. This detail reshapes everything that follows. In electromagnetism, photons carry no electric charge, so the electromagnetic field does not interact with itself. In QCD, gluons interact with other gluons. The field binds itself together. Energy no longer disperses evenly through space. It organizes. When two quarks sit close together inside a proton, the gluon field between them is compact and relatively low in energy. Calculations show that under these conditions, quarks behave almost independently. This regime is visible in high-energy collisions, where quarks briefly act as if the strong force has loosened. But as separation increases, the picture changes sharply. Instead of spreading out, the gluon field contracts into a narrow region connecting the quarks. This structure is commonly referred to in theory and simulation as a flux tube. Its behavior has been studied extensively using lattice QCD. Lattice calculations place quarks on a discretized grid of spacetime and compute how the gluon field behaves between them. The results are consistent across methods and computing platforms. Energy accumulates linearly with distance. Quantitatively, the energy stored in the flux tube increases by roughly 1 giga-electron-volt for every femtometer of separation. A femtometer is 1/1,000,000th of a nanometer. At such scales, energy rises quickly. This increase cannot continue indefinitely. At a certain point, the energy concentrated in the field exceeds the energy required to create new matter. When that threshold is reached, the field reorganizes. A quark and an antiquark appear from the energy stored in the flux tube. The original connection splits into two shorter connections. The system ends with two composite particles instead of one separated quark. This process has been observed indirectly countless times. In particle detectors, it appears as hadronization. Quarks produced in collisions never arrive alone. They fragment into jets, cascades of hadrons whose structure preserves the original momentum flow. Every modern collider confirms this behavior. Experiments at CERN provide especially clear evidence. When protons collide at tera-electron-volt energies in the Large Hadron Collider, quarks inside them scatter violently. Detectors track thousands of resulting particles. The patterns match QCD predictions in detail. Jets emerge as narrow cones. Their energies, angular distributions, and correlations reflect the dynamics of quarks and gluons before confinement takes over. Yet not a single quark escapes the process. This outcome is not dependent on experimental design. It arises from the mathematics of the theory. The equations governing the gluon field do not permit isolated color charge. Confinement is not imposed, it emerges. Historically, this behavior puzzled physicists deeply. In the 1960s, the idea that a force could strengthen with distance seemed implausible. Forces were expected to dilute, not concentrate. QCD overturned that expectation decisively. The breakthrough came in 1973, when David Gross, Frank Wilczek, and David Politzer discovered asymptotic freedom. Their calculations showed that the strong interaction weakens at extremely short distances. At larger distances, it strengthens. This dual behavior explained two previously conflicting observations. High-energy scattering experiments showed quarks behaving almost freely. At the same time, no experiment ever observed an isolated quark. Both results followed from the same equations. Asymptotic freedom was not merely a clever idea, it was tested rigorously. Predictions matched data from SLAC, CERN, and later from electron-proton colliders such as Hera. The agreement was precise. Confinement, however, resisted direct mathematical proof for many years. Unlike asymptotic freedom, it could not be derived cleanly, using simple approximations. Its reality emerged through computation. With the rise of powerful supercomputers in the 1980s and 90s, lattice QCD simulations became increasingly accurate. These simulations demonstrated that confinement arises naturally from gluon self-interaction. No alternative behavior appeared. The strong force, unlike gravity or electricity, does not act as a messenger across empty space. It acts as a binding network that reshapes space between quarks. Separation does not create freedom, it creates tension. This property has consequences far beyond particle physics laboratories. In neutron stars, matter is compressed to densities where quarks are forced into extreme proximity. The behavior of the strong interaction under such conditions shapes the star's structure and stability. Astrophysical observations depend on these interactions indirectly. NASA and ESA missions that study neutron stars and gravitational waves rely on models rooted in QCD. When detectors measure signals from neutron star mergers, the interpretation depends on how quark matter responds to stress. The same force that confines quarks governs cosmic extremes. Inside ordinary matter, confinement ensures stability. Protons do not decay, nuclei hold together, atoms persist for billions of years. Without confinement, matter as we know it would not exist. The strong force achieves this stability not by gentleness, but by refusal. It does not allow partial separation. It does not allow leakage. Every attempt to pry quarks apart strengthens the very connection being challenged. Physicists sometimes describe confinement as a property of the vacuum itself. The ground state of the gluon field resists the presence of isolated color charge. The resistance is structural, not reactive. This view aligns with decades of experimental evidence. No environment, no energy scale, no natural process has ever produced a free quark. Searches in cosmic rays, in lunar material, and in accelerated debris all agree. What makes this remarkable is its consistency. The strong interaction behaves the same way everywhere it has been tested. Its rules do not soften with context. Carl Sagan once wrote, "Nature is always more subtle, more intricate, more elegant than what we are able to imagine." In QCD consideration, that subtlety takes a concrete form. The force that binds matter strengthens when challenged. This is not an aesthetic choice. It is a mathematical consequence of how color charge and gluon self-interaction are structured. The equations allow no alternative outcome. As experiments continue to refine measurements and simulations grow more precise, the picture only sharpens. Confinement remains intact. Flux tubes remain real. Hadronization remains unavoidable. The strong force continues to behave unlike any other. Once this behavior is taken into account, the internal picture of hadrons can no longer remain simple. Quarks are permanently confined, and the force binding them intensifies with separation, leaving no room for a static interior. Inside particles, such as the proton, interactions must remain active at all times, sustained by fields and exchanges that never settle into fixed positions. Under these conditions, the familiar image of three quarks becomes insufficient, replaced by a dense and dynamic structure shaped by a deeper property of the strong interaction. Part 4. What is color? If it has nothing to do with light, yet decides what matter can be. There is a property that no telescope can detect, no camera can record, and no human sense can perceive, yet it decides whether matter can exist in stable form at all. That property is called color, and without it, protons would not hold together, nuclei would not survive, and quarks would never remain bound long enough to form anything familiar. Color entered physics not through observation, but through necessity. In the early 1960s, physicists faced a growing problem. Experiments were discovering more and more hadrons, particles made of quarks, and patterns were emerging that demanded a deeper organizing principle. Certain particles appeared to violate the Pauli exclusion principle unless quarks possessed an additional hidden property. Murray-Gell-Mann and others realized that quarks needed an extra label beyond electric charge and spin. This label could not correspond to anything directly observable because no experiment had ever seen it. It existed to make the mathematics consistent and the data intelligible. The name chosen was color, not because it resembled light, but because it allowed three distinct states to be discussed without implying hierarchy. Red, green, and blue were convenient placeholders, nothing more. From the beginning, color was bookkeeping with consequences. Once color was introduced, the strong interaction could be described with a new symmetry structure known as SU3. This mathematical framework dictated how quarks and gluons interact. Unlike electric charge, which comes in one type with positive and negative signs, color comes in three types, and they interact in a far more intricate way. Gluons sit at the center of this complexity. In electromagnetism, photons carry force but no electric charge. In quantum chromodynamics, gluons carry color themselves. This single fact transforms the strong interaction into a self-interacting system. Because gluons carry color, they interact not only with quarks but also with each other. The field becomes nonlinear. Energy flows do not spread smoothly through space. They fold, reinforce, and reorganize. This behavior has no counterpart in everyday forces. Early calculations hinted at this, but the full implications became clear only with the development of quantum chromodynamics in the 1970s. The equations showed that color forces intensify as quarks separate. This was not an assumption. It emerged directly from the structure of the theory. The gluon field does not allow isolated color charge. Whenever color imbalance appears, the field responds by rearranging itself until neutrality is restored. This is why all observed particles are color neutral. Protons achieve this neutrality by combining three quarks, each with a different color. Mesons achieve it by pairing a quark with an antiquark, carrying the corresponding anticolor. No confirmed particle violates this rule. The importance of this principle became unmistakable through experiments. Deep inelastic scattering at SLAC revealed quarks behaving as if they were free at short distances, yet every attempt to isolate them failed. Color explained why. As separation increases, the gluon field between quarks does not weaken. It tightens into a narrow region of concentrated energy. Lattice QCD simulations later confirmed this behavior numerically, using supercomputers to solve the equations step by step. The field behaves like a stretched structure, storing energy rather than releasing it. When enough energy accumulates, the field reorganizes by creating new quark-antiquark pairs. Color neutrality is preserved. Isolation is avoided. This process repeats without exception. At CERN, this behavior is observed indirectly in every high-energy collision. Quarks and gluons scatter, but what reaches the detectors are jets of hadrons. The pattern of these jets carries the imprint of color interactions. Physicists can trace how energy flowed through colored particles before confinement reshaped the outcome. The agreement between theory and observation is precise. Color does its work invisibly, yet decisively. The idea that an unseen property governs such outcomes initially met resistance. Physics had long relied on quantities tied to measurement. Color challenged that tradition. Its success forced a shift in perspective. Color is not an optional feature layered onto quarks. It defines how quarks exist at all. Without color, the strong interaction collapses into inconsistency. Matter as we know it disappears. This insight gained further support as lattice QCD matured. By the 1980s and 90s, simulations showed how gluon self-interaction produces confinement naturally. No extra assumptions were required. The vacuum itself takes on structure in this picture. The lowest energy state of the gluon field resists isolated color. Attempts to introduce imbalance raise the energy of the entire system. Neutrality becomes the only stable outcome. The consequences reach far beyond particle accelerators. Inside neutron stars, matter is compressed to densities where quarks are forced into extreme proximity. Color interactions shape the behavior of this matter under enormous pressure. Astrophysical models rely on these interactions indirectly. NASA and ESA missions studying neutron stars and gravitational waves interpret their data through equations that include QCD effects. The way color operates at subatomic scales influences objects tens of kilometers across. Microscopic rules leave macroscopic signatures. Inside an ordinary proton, color drives constant rearrangement. Gluons split into quark-antiquark pairs and recombine. Momentum flows between constituents. The proton remains stable, not because it is static, but because color enforces balance. This dynamic interior replaced older images of particles as rigid containers. The proton became a system defined by ongoing exchange rather than fixed contents. Color governs every exchange. Richard Feynman once said, "The theory of quantum electrodynamics describes nature as absurd from the point of view of common sense. The same applies even more strongly to color in QCD. Common sense has no place at this scale." Yet the results are not vague or approximate. Predictions derived from color dynamics match experimental measurements to remarkable accuracy. Precision replaces intuition. The strength of color interactions explains why quarks behave freely at short distances and remain bound at larger ones. This dual behavior underpins the stability of matter. Without it, atoms could not persist. Color also explains why gluons dominate the internal energy of protons. Measurements show that gluons carry most of a proton's momentum. Their self-interaction fills the interior with activity. Quarks provide identity. Gluons provide substance. The language of color may sound abstract, but its consequences are concrete. Every nucleus owes its existence to color neutrality. Every chemical element rests on this unseen rule. The world is built on interactions no eye can see. As experiments continue and simulations grow more refined, color remains central. No alternative framework has matched its explanatory power. Its role in confinement remains unchallenged. As color interactions continuously rearrange the interior of the proton, the familiar picture of particles as simple assemblies can no longer hold. Fields and exchanges remain active at all scales, preventing any fixed configuration from settling in place. What appears instead is a system dominated by motion and constant exchange, where quarks, antiquarks, and gluons contribute simultaneously to the proton's properties. Under these conditions, the notion of a proton made of only 3 quarks becomes incomplete, replaced by a densely populated interior shaped by ongoing dynamics rather than static parts. Part 5 is a proton really, 3 quarks or a sea that never stops moving. If a proton could be held still for a single instant, the familiar picture of 3 quarks might no longer describe what dominates its interior. At the scales where experiments actually probe, the proton reveals something far more crowded, far more active, and far less static than any simple diagram suggests. For much of the 20th century, the proton was introduced as a tidy object, 3 quarks bound together, their charges adding up neatly, their spins combining to produce a stable particle. This picture was not wrong, but it was incomplete. It described identity, not activity. The turning point came from the same class of experiments that first exposed quarks at all. Deep inelastic scattering showed that when electrons struck protons at high energies, the response depended strongly on how momentum was distributed inside. What emerged was not a fixed internal layout, but a shifting pattern. At SLAC, and later at CERN, researchers found that the momentum of a proton is not carried mainly by its three valence quarks. Instead, most of it belongs to gluons. This result was unexpected at first, then unavoidable. Gluons do more than bind quarks together. Because they carry color charge themselves, they interact continuously, splitting and recombining inside the proton. In the process, they generate short-lived quark-antiquark pairs. These pairs appear and vanish on timescales far shorter than any direct measurement. The proton, seen through modern experiments, resembles a dense environment rather than a compact assembly. Gluons fill its interior. Quark-antiquark pairs flicker into existence. Momentum flows constantly between constituents. Nothing remains fixed for long. Physicists describe this behavior using parton distribution functions, usually shortened to PDFs. These functions do not track individual particles. They describe probabilities. At a given energy scale, they tell how likely it is that a quark or gluon carries a certain fraction of the proton's momentum. Mapping these distributions took decades. Each new experiment refined them. Each increase in collision energy shifted the balance further toward gluons. At the energies reached by the Large Hadron Collider, gluons dominate overwhelmingly. This dominance changes how the proton must be understood. The three valence quarks still define its quantum numbers. They set its electric charge and baryon number, but they do not account for most of what happens inside. A useful way to think about this emerged gradually in the 1980s and 90s. The proton was no longer treated as a container holding particles. It was treated as a dynamic system governed by quantum chromodynamics. Its structure depended on the energy scale at which it was examined. At lower energies, the three-quark picture works reasonably well. At higher energies, the picture dissolves into a dense network of gluons and transient pairs. Both descriptions are correct within their domains. This scale dependence is not an inconvenience. It is a feature of QCD. As the resolution of an experiment increases, more of the proton's internal activity becomes visible. The interior does not simplify under scrutiny. It becomes busier. The Large Hadron Collider provided a striking demonstration of this behavior. When protons collide at tera-electron-volt energies, the interactions are dominated by gluon-gluon collisions. The quarks that define the proton's identity often play only a secondary role. Detectors such as ATLAS and CMS record the aftermath as jets of particles spreading outward. The shapes and energies of these jets reflect the momentum carried by gluons inside the proton before the collision. The data leave little doubt about who dominates the interior. This understanding reshaped how physicists interpret mass itself. The intrinsic masses of the valence quarks account for only a small fraction of the proton's total mass. Most of the mass arises from energy stored in gluon fields and in the motion of quarks and antiquarks. In practical terms, this means that the proton's mass is not the sum of its parts in any straightforward sense. It is the result of continuous interaction. Stability emerges from activity, not from stillness. Historical context makes this shift clearer. Early nuclear models treated protons as rigid objects. As experimental tools improved, rigidity gave way to motion. The proton became less like a building block and more like a process. Theoretical work reinforced this view. Lattice QCD simulations showed that gluon fields inside hadrons fluctuate intensely, even in their lowest energy states. There is no quiet interior where constituents sit passively. These simulations required immense computational effort. Teams spent years refining algorithms and increasing resolution. The result was consistent across independent groups. The proton's interior remained dense and active under every test. Astrophysical observations give indirect support to this picture. When NASA and ESA study cosmic rays, they measure protons accelerated to energies far beyond those produced on Earth. The way these protons interact with interstellar matter reflects the same internal structure measured in laboratories. Even in extreme environments, the proton does not simplify. Its interior activity persists. The rules of QCD do not relax with context. One of the more subtle insights from PDF studies concerns momentum sharing. At high energies, gluons carry most of the proton's momentum, but they do not carry its defining quantum numbers. Identity and substance are separated roles. The valence quarks act as anchors for identity. Gluons provide the majority of momentum and energy. Short-lived quark-antiquark pairs contribute constantly but transiently. The proton persists as a recognizable entity through this constant turnover. This persistence puzzled physicists at first. How could an object remain stable if its interior was so active? The answer lay in confinement and color neutrality. QCD enforces balance at every moment. No constituent can escape. No imbalance can grow unchecked. The activity is constrained, channeled, and recycled within strict limits. Order emerges from constraint rather than from simplicity. The textbook image of three quarks was never meant to describe this internal complexity. It was a starting point. Modern experiments moved far beyond it. This shift in understanding required a shift in language. Physicists stopped asking where quarks are located inside a proton. They began asking how momentum and energy flow through it. The proton became something defined by distributions, not positions. Carl Sagan once wrote, "Science is a way of thinking much more than it is a body of knowledge." In this case, the change in thinking mattered as much as the data themselves. The proton was reimagined without losing precision. Nothing in this picture contradicts the existence of valence quarks. Instead, it places them within a broader framework where they coexist with a far larger cast of participants. The simplicity lies in the rules, not in the outcome. As measurements continue and models grow more refined, the proton's interior remains a place of constant exchange. No experiment has ever revealed a moment of stillness within it. When the interior of the proton is dominated by gluons and short-lived quark-antiquark pairs, mass and stability can no longer be traced to fixed constituents alone. The largest contribution must arise from how energy is stored, exchanged, and confined by the strong interaction itself. In this regime, mass stops behaving like a simple sum of particle masses and instead reflects the dynamics of fields, motion, and binding energy operating continuously inside matter. Part 6. If quarks are almost massless, why are you heavy? Here is a result that overturns a deeply rooted assumption. The quarks inside your body contribute only a small fraction of your mass, yet the total mass of ordinary matter remains large, stable, and persistent across the universe. The difference does not come from hidden particles. It comes from energy organized in a very specific way. For many years, mass was described as something intrinsic, a property carried by particles themselves. This view worked well for atoms and molecules, where adding constituents increased weight in a predictable way. At the level of quarks, that intuition breaks down. Measurements show that an up quark has a mass of only a few mega-electron volts. A down quark is only slightly heavier. Together, the three valence quarks inside a proton account for less than 10% of the proton's total mass. Yet a proton weighs about 938 mega-electron volts. This gap forced physicists to look elsewhere. The answer emerged not from new particles, but from motion and interaction. In quantum chromodynamics, mass arises largely from energy stored in fields and in the movement of quarks and gluons, confined within a tiny region. The idea has roots in early 20th century physics. Albert Einstein showed that energy and mass are equivalent. Energy confined in a system contributes to its inertia. In the proton, that equivalence becomes dominant. Inside a proton, quarks move rapidly. Gluons fill the interior, constantly exchanging momentum. The strong interaction binds everything together so tightly that enormous energy becomes trapped within a space smaller than 1 femtometer. That trapped energy accounts for most of the proton's mass. This understanding developed gradually. In the 1970s, experiments revealed that quarks behave almost as if they are massless at high energies. At the same time, hadrons remained heavy. The contradiction pushed theorists toward a deeper explanation. Quantum chromodynamics provided it. The theory showed that even if quarks had zero intrinsic mass, confinement alone would generate massive bound states. Mass became an emergent property rather than a simple sum. Lattice QCD simulations later confirmed this picture quantitatively. By computing the energy stored in gluon fields and quark motion, physicists reproduced the observed masses of protons and neutrons without inserting large quark masses by hand. The agreement strengthened confidence in the theory. This does not mean intrinsic mass plays no role. The Higgs field contributes to the masses of quarks and electrons. Experiments at CERN confirmed the Higgs mechanism in 2012. But for visible matter, its contribution is modest. The Higgs field explains why quarks have non-zero mass at all. QCD explains why bound states made of those quarks are heavy. Both mechanisms operate together, but on very different scales. This distinction matters for understanding everyday matter. When you step on a scale, the reading reflects the mass of protons and neutrons in your body. Those masses come mostly from QCD binding energy, not from the Higgs field. The weight you feel is energy organized at subatomic scales. Historical experiments make this clear. In deep inelastic scattering, electrons probe the proton's interior. The response reveals energetic constituents whose motion contributes to the proton's inertia. These experiments showed that momentum and energy are distributed dynamically. At the Large Hadron Collider, collisions further confirmed this picture. When protons collide, the energy released reflects the internal energy stored by confinement. The debris patterns match predictions based on QCD dynamics. This understanding also reshaped cosmology. NASA and ESA observations show that ordinary matter accounts for only about 5% of the universe's total energy content. Within that 5%, most mass arises from the same mechanism operating inside every proton. Galaxies shine because of nuclear reactions. Those reactions depend on proton and neutron masses. Those masses depend on QCD. A chain links subatomic energy to cosmic structure. Physicists sometimes describe this as mass without matter. The phrase is shorthand, not metaphor. It means that energy confined by the strong interaction behaves exactly like mass. It resists acceleration. It responds to gravity. This idea was difficult to accept at first. Early particle models favored tangible constituents. Fields and motion seemed abstract by comparison. Experiments left no alternative. The proton's mass is remarkably stable. Despite constant internal motion, its mass remains fixed to high precision. Confinement ensures that energy stays bound. This stability has consequences across physics. Nuclear binding energies, atomic masses, and chemical behavior all depend on proton and neutron masses. The strong interaction quietly shapes every material property. The story also clarifies why mass scales differ so dramatically. An electron is much lighter than a proton because it does not experience the strong interaction. It lacks access to the same reservoir of confined energy. In this sense, mass becomes contextual. It depends on which interactions a particle participates in. For quarks, confinement dominates. Lattice QCD continues to refine this picture. Modern simulations calculate hadron masses with increasing precision, matching experimental values within small uncertainties. Each success reinforces the same conclusion. The mass of ordinary matter is not a static inventory of particles. It is the outcome of continuous interaction governed by QCD. Energy, not substance, carries the load. This realization shifts how composition is understood. Asking what we are made of becomes inseparable from asking how energy is organized and constrained. Particles provide structure, interactions provide weight. Carl Sagan once wrote, "We are a way for the cosmos to know itself." At the level of mass, the cosmos expresses itself through confined energy shaping stable matter. The statement gains precision here. Nothing in this picture relies on conjecture. It is anchored in decades of accelerator experiments, lattice simulations, and observations that track how quarks and gluons behave across a wide range of energies and scales. Across these independent approaches, the same result persists. Most of the mass of ordinary matter arises from QCD dynamics, rather than from the bare masses of quarks themselves. When mass is dominated by QCD energy, changes in how quarks and gluons behave under extreme conditions cannot be treated as minor corrections. Variations in temperature, density, or collision energy reshape the same interactions that give matter its stability, pushing familiar structures toward regimes where their usual descriptions begin to fail. At those limits, the behavior of quarks and gluons departs sharply from anything observed in everyday matter, marking the edges of what current experiments and theory can fully describe. Part 7. Did we invent the word quark before we understood what it would cost us? A scientific object received its name before anyone knew that it would never appear alone, and that choice would quietly shape how generations tried to understand it. The word was introduced lightly, almost playfully, long before the consequences of the idea were fully revealed. In the early 1960s, particle physics was facing a problem of abundance. Accelerators were discovering new hadrons at a pace that made simple classification impossible. Protons, neutrons, pions, kaons, lambdas, sigmas, deltas, and many more filled the experimental records. Patterns were visible, but the organizing principle was missing. Murray Gell-Mann approached this problem with structure rather than accumulation. He noticed that many hadrons could be arranged into families with shared properties, much like the periodic table had once organized chemical elements. In 1961, this became known as the Eightfold Way. The Eightfold Way worked remarkably well. It predicted relationships between particles that had already been observed, and it even pointed toward particles not yet discovered. But it also raised an uncomfortable question. If hadrons followed such regular patterns, perhaps they were not elementary after all. Perhaps they were built from something smaller. In 1964, Gell-Mann proposed exactly that. He suggested that hadrons were composed of more fundamental entities carrying fractional electric charge. 3 of them would combine to form baryons, 2 would combine to form mesons. This proposal was initially cautious. At first, these entities were treated as mathematical devices. They explained symmetry patterns and quantum numbers, but Gell-Mann did not insist they were physically real. The name he chose reflected that hesitation. The term quark came from James Joyce's novel, Finnegan's Wake, specifically the line, 3 quarks for muster mark. Gell-Mann liked the sound of the word and its suggestion of threeness. It fit the structure of baryons neatly. At the time, this choice carried no warning. Many theoretical constructs had come and gone in physics. Names often outlived the ideas that inspired them. No one expected this one to harden into reality. Almost immediately, resistance followed. Fractional electric charge had never been observed. No experiment had detected an isolated object with 1/3 of the electron's charge. Many physicists assumed quarks were merely bookkeeping tools. Gell-Mann himself shared this caution. In early papers, he described quarks as possibly fictitious, useful for classification but not necessarily real particles. The name remained. The interpretation stayed flexible. That flexibility vanished as experiments advanced. In the late 1960s, deep inelastic scattering experiments at SLAC struck protons with electrons at unprecedented energies. The results forced a re-evaluation. Protons responded as if they contained point-like constituents. Momentum transfer patterns showed sharp features that could not be explained by a smooth internal charge distribution. Richard Feynman described these constituents as partons. Within a few years, it became clear that partons and quarks were the same entities viewed through different theoretical lenses. The mathematical tools had found physical footing. At that moment, the name quark shifted from convenience to commitment. The objects it described were no longer optional. They were required by data. Yet something peculiar followed. As evidence for quarks accumulated, so did evidence that they could never be isolated. Experiments searched directly for free quarks carrying fractional charge. None were found. Searches extended to cosmic rays, accelerator debris, and even lunar soil returned by NASA missions. Every search failed in the same way. The signature was absent, not ambiguous. The invisibility was systematic. By the early 1970s, quantum chromodynamics had taken shape. It explained why quarks appeared point-like in scattering experiments and why they refused to appear alone. Color charge and gluon self-interaction changed the rules of separation. In retrospect, the name quark carried an irony no one could have anticipated. It labeled something that would define matter while remaining permanently indirect. The word became common. The object stayed elusive. Historical correspondence shows that Gell-Mann recognized this tension. In later reflections, he acknowledged that quarks had moved from abstraction to reality without gaining visibility. The name endured because the structure endured. This pattern is not unique in science, but it is rare. Often, names follow understanding. In this case, the name arrived first, and understanding chased it for decades. The cost became apparent only afterward. Once quarks were accepted as real, physicists had to abandon the expectation that fundamental constituents must be directly observable. Evidence would come through behavior, not isolation. Jets in particle detectors became stand-ins. Momentum distributions replaced images. Statistical agreement carried the weight of confirmation. The word stayed simple, the reality did not. This shift required a cultural adjustment within physics. Earlier generations had learned by seeing tracks in cloud chambers or bubbles in liquid. Quarks offered no such reassurance. Instead, they demanded trust in patterns repeated across experiments and energies. Each dataset reinforced the same conclusion. The absence became meaningful. Carl Sagan once wrote, "Extraordinary claims require extraordinary evidence." In the case of quarks, the evidence accumulated not as sightings, but as constraints. Every attempt to contradict confinement failed. The name quark also shaped public perception. Its unusual sound suggested something exotic, almost whimsical. That impression contrasted sharply with the rigidity of the physics it represented. As quantum chromodynamics matured, quarks became indispensable. Predictions of hadron masses, decay rates, and scattering cross-sections depended on them. Removing quarks from the theory collapsed its predictive power. The irony deepened. A word borrowed from experimental literature described objects that could never be extracted experimentally. Language stayed accessible, nature did not. By the 1980s, few physicists doubted the reality of quarks. The debate had shifted entirely. The question was no longer whether quarks exist, but how their confinement shapes everything built from them. The name faded into familiarity. The implications continued to unfold. Looking back, the naming moment now appears as a hinge point. Had the entities been given a more technical label, their invisibility might have seemed less surprising. Instead, the casual word made the constraint more striking. This is not a story of mistake. It is a story of timing. The name arrived before the rules were known. The rules turned out to be absolute. Physics adapted around them. Today, quarks sit at the foundation of the Standard Model. They define the structure of visible matter. Their interactions generate mass. Their confinement ensures stability. They remain unseen, yet indispensable. The cost of the name was not confusion, but commitment. Once quarks were defined as physical entities, theory and experiment were bound to follow the evidence wherever it led, even when that path moved away from direct observation. The term remained in use, and so did the boundary it described. As experiments extend across wider energy ranges, additional layers of behavior appear around quarks rather than inside them. Their properties are revealed through changes in interaction strength, with scale, momentum transfer, and distance, not through any internal structure. At sufficiently short distances, The same strong interaction that enforces confinement at larger scales weakens instead, overturning expectations built from every other known force. In this regime, confinement and apparent freedom exchange roles in a way no earlier framework had anticipated. Part 8. Asymptotic freedom. Why do quarks behave free only when they're trapped? The strong force reveals its most unsettling behavior at the moment you expect it to behave normally, because when quarks are forced extremely close together, the interaction that binds them appears to weaken rather than intensify. This reversal stands against nearly every physical instinct built from gravity, electricity, and everyday experience. To understand how this came to light, it helps to return to the state of particle physics at the end of the 1960s. Experiments at SLAC had already shown that protons contained point-like constituents. Scattering results suggested that at very high energies, these constituents responded almost as if they were not tightly bound at all. This behavior puzzled theorists because confinement had already become difficult to ignore. At first glance, the data seemed contradictory. On one hand, quarks never appeared in isolation. On the other hand, high-energy collisions treated them as nearly independent objects. Something fundamental was missing from the theoretical picture. That missing piece arrived in 1973. David Gross and Frank Wilczek at Princeton, and independently David Politzer at Harvard, examined how the strength of the strong interaction changes with energy scale. What they found overturned expectations. Their calculations showed that the effective strength of the strong interaction decreases as quarks approach one another. At very short distances, or equivalently at very high energies, quarks interact only weakly. They behave almost as if they are free. This property became known as asymptotic freedom. The name reflects behavior at extremes rather than absolute conditions. Freedom appears only asymptotically, only when distances shrink towards zero. At larger separations, the interaction grows stronger. The discovery was not a guess. It followed directly from the structure of quantum chromodynamics. Because gluons carry color charge, their self-interaction alters how the force evolves with scale. This feature has no counterpart in electromagnetism. In practical terms, this meant that QCD could explain two experimental realities at once. Deep, inelastic scattering showed quarks acting almost independently. At the same time, confinement prevented them from ever escaping. Both behaviors arose from the same equations. The impact was immediate. Asymptotic freedom made it possible to calculate high-energy processes involving quarks and gluons with precision. Predictions for scattering rates, jet formation, and momentum distributions became reliable. Agreement with experimental data strengthened rapidly. By the time experiments at CERN and later at Hera tested these predictions, the match was unmistakable. High-energy collisions behaved exactly as asymptotic freedom required. The theory held. This achievement earned Gross, Wilczek, and Politzer the Nobel Prize in 2004. The citation recognized how asymptotic freedom explained the behavior of quarks at both short and long distances. It resolved a central tension in particle physics. Yet the deeper implication went beyond technical success. Asymptotic freedom implied that the strong force has two distinct regimes. Near contact, it loosens. With separation, it tightens. The same interaction produces opposite effects depending on scale. This dual behavior reshaped how physicists thought about forces altogether. Forces were no longer static features. They evolved with context. Strength became a function of distance and energy. Inside a proton, quarks are confined within a region smaller than 1 femtometer. At that scale, asymptotic freedom allows them to move with relative independence. This explains why scattering experiments see sharp, point-like responses. At the same time, the proton remains stable because quarks cannot drift apart. As soon as separation increases, the interaction strengthens, pulling them back together through the gluon field. Freedom exists only inside confinement. This pairing of effects initially seemed paradoxical. How could quarks be free and bound at the same time? The resolution lay in understanding that freedom was local and conditional. It did not imply escape. High-energy collisions illustrate this clearly. When protons collide at the Large Hadron Collider, quarks inside them scatter violently. During the brief interaction, asymptotic freedom dominates. Calculations treat quarks as nearly free participants. Moments later, confinement takes over. Quarks and gluons reorganize into jets of hadrons. The freedom vanishes as distance grows. Detectors record only composite particles. This sequence repeats in every collision. It is not an approximation. It is the expected outcome of QCD. Precision measurements confirm it, event after event. Theoretical understanding of this behavior required abandoning simple pictures of force. Instead of imagining forces as elastic bands or invisible pulls, physicists began thinking in terms of fields whose properties change with scale. QCD demanded that shift. The vacuum itself plays an active role. At short distances, the vacuum screens color charge weakly. At larger distances, the gluon field organizes into structures that resist separation. The vacuum becomes part of the interaction. This idea gained support from lattice QCD simulations. By calculating interactions on a discretized spacetime grid, physicists showed how asymptotic freedom and confinement arise from the same underlying dynamics. No adjustment was needed. The simulations also clarified why asymptotic freedom cannot be observed directly. It appears only inside bound systems or during extremely brief interactions. There is no regime where quarks are both free and observable. This limitation shapes experimental strategy. Physicists do not attempt to isolate quarks. They infer their behavior from patterns in collisions. Asymptotic freedom makes those inferences reliable. The consequences extend beyond laboratories. In the early universe, temperatures and energies were far higher than anything achieved today. Quarks moved within a quark-gluon plasma, where asymptotic freedom dominated. As the universe cooled, confinement took hold. Experiments at CERN have recreated this transition on microscopic scales by colliding heavy ions. The resulting plasma behaves as QCD predicts, flowing collectively at first and then condensing into hadrons. The behavior reflects the same scale dependence discovered in the 1970s. NASA and ESA observations of cosmic rays also reflect this physics indirectly. When ultra-high-energy protons strike Earth's atmosphere, their interactions follow patterns shaped by asymptotic freedom at short distances. The resulting particle showers carry QCD's signature. Asymptotic freedom also explains why QCD calculations become simpler at high energies. Perturbative methods work because interactions weaken. At lower energies, calculations grow complex as confinement dominates. This separation of regimes defines much of modern particle physics. High-energy processes can be computed precisely. Low-energy bound states require numerical methods and simulation. The theory accommodates both. The discovery also altered expectations about unification. Some hoped the strong force might weaken entirely at small scales, allowing quarks to escape. Asymptotic freedom showed that this would never happen. Freedom is limited, not absolute. In this sense, asymptotic freedom imposed a boundary as firm as confinement itself. Quarks could behave independently, but only while remaining trapped. The rule was strict. Carl Sagan once wrote that understanding often comes from recognizing patterns that persist across scales. Asymptotic freedom is one such pattern. It governs the smallest distances and shapes the largest outcomes. Today, no alternative theory has reproduced this behavior with the same accuracy. QCD remains unique in predicting a force that weakens at short range and strengthens at long range. Its success is empirical, not aesthetic. The strong force does not behave strangely by accident. Its behavior is encoded in the mathematics of color charge and gluon self-interaction. The equations leave little room for interpretation. Asymptotic freedom accounts for why quarks can be treated as nearly free at short distances in calculations. while never appearing as free objects in nature. The two behaviors arise from the same interaction and cannot be separated experimentally. When freedom exists only at extreme proximity, the transition between weak and strong coupling must leave measurable signatures. In high-energy collisions, these signatures appear as jets, correlations, and momentum patterns recorded by detectors rather than as isolated particles. Such features provide direct experimental access to quark behavior without ever producing a single free quark, shifting the focus from theoretical description to observable evidence. Part 9. Have we ever seen quarks at all, or only their shadows in detectors? Every quark that has ever been produced in a laboratory has vanished before it could reach an instrument, leaving behind only patterns that had to be learned slowly, patiently, and with care. From the very beginning, evidence for quarks arrived not as objects, but as traces that demanded interpretation. When early particle detectors were built, many physicists expected discovery to look familiar. In cloud chambers and bubble chambers, particles left visible tracks. You could point to a curved line and say, this is an electron, this is a muon. Quarks refused to cooperate with that expectation. Deep inelastic scattering at SLAC had already shown that something point-like lived inside protons. Momentum transfer patterns were clear. The internal response was unmistakable. Yet no isolated track ever appeared. As accelerators grew more powerful, the situation became even more striking. At higher energies, collisions did not simplify the picture, they complicated it. Instead of single particles, detectors recorded cascades. These cascades became known as jets. When a quark or gluon is struck hard in a collision, it cannot remain alone. As it moves away from the interaction point, confinement takes over. Energy in the gluon field converts into new particles. What reaches the detector is a narrow spray of hadrons moving in roughly the same direction. At first, jets were unexpected. Early detectors were not designed to interpret them. Physicists had to learn new ways of seeing. Patterns replaced tracks. By the late 1970s, jet structure had become a central tool. Experiments at CERN's superproton synchrotron showed clear 2-jet and 3-jet events. These patterns matched predictions for quarks and gluons produced in high-energy collisions. A turning point came when 3-jet events were observed. 2 jets corresponded naturally to a quark and an antiquark. The third matched the behavior expected of a radiated gluon. This was the first direct experimental signature of gluons. No one saw a gluon. What they saw were jets, whose angles and energies fit QCD calculations with precision. Agreement replaced visibility. As detectors improved, so did confidence. Modern experiments at the Large Hadron Collider record millions of collisions per second. Each event is reconstructed from energy deposits, timing information, and correlations across detector layers. From this, physicists infer the presence of quarks and gluons with remarkable accuracy. The process is statistical, not visual. A single event does not prove anything by itself. Evidence accumulates across vast datasets. Patterns that repeat without deviation become decisive. Jets are not random sprays. Their internal structure reflects the type of particle that initiated them. Quark-initiated jets differ subtly from gluon-initiated jets. These differences can be measured and compared with theory. Momentum distributions inside jets follow precise rules. Angular spreads match predictions from asymptotic freedom. Energy loss patterns reflect confinement. Every feature ties back to QCD. Hadronization, the process by which quarks and gluons transform into hadrons, was once treated as a complication. Over time, it became a source of insight. Its regularities revealed how confinement operates in practice. Monte Carlo simulations played a crucial role here. Physicists encoded QCD rules into computational models that generated synthetic collision events. When these simulations reproduced detector data, confidence in the underlying theory grew. The success was not limited to one experiment or one energy scale. From early electron-positron colliders to modern proton-proton collisions, the same signatures appeared. Consistency became the strongest argument. At the LHC, detectors such as ATLAS and CMS measure jet energies with extreme precision. Calorimeters capture the total energy. Tracking systems reconstruct particle trajectories. From these components, the invisible becomes constrained. Missing energy also plays a role. When momentum does not balance in an event, physicists infer the presence of particles that escape detection. The method depends on knowing how quarks and gluons behave. Quarks themselves are never the missing objects. They transform before leaving the interaction region. What remains missing are neutrinos or other weakly interacting particles. This distinction matters. It reinforces the conclusion that quarks always leave indirect signatures, never direct ones. Their presence is inferred through what they produce. Historical skepticism faded gradually. Early critics argued that indirect evidence could always be reinterpreted. Over time, the precision of predictions narrowed that freedom. Alternative explanations failed. By the 1980s, few doubted that jets were the experimental face of quarks and gluons. The correspondence was too detailed, too consistent. Evidence had matured. This way of knowing reshaped experimental culture. Particle physics moved from photography to reconstruction. Seeing gave way to measuring. Confidence came from redundancy and cross-checks. Each detector component confirmed the others. Each experiment confirmed the previous ones. The picture stabilized. NASA and ESA do not study quarks directly, yet their instruments rely on similar logic. Cosmic ray detectors infer primary particles from air showers. Gamma-ray telescopes reconstruct sources from secondary signals. Indirect evidence governs much of modern science. In that context, quarks are not unusual. What makes them distinctive is the completeness of their indirect signatures. Every predicted feature has been observed somewhere. Carl Sagan once wrote, "Absence of evidence is not evidence of absence." In the case of quarks, the situation is reversed. Absence of direct appearance is itself predicted evidence. The theory requires it. Jets also reveal differences between quarks and gluons. Gluon jets tend to be broader, producing more particles. Quark jets are narrower. These distinctions match QCD expectations precisely. Such details leave little room for doubt. The theory does not merely explain that quarks exist, it explains how they must appear. Indirectly, collectively, and repeatedly. Even searches beyond the standard model rely on this foundation. New particles are proposed based on deviations from known jet patterns. Understanding quarks is essential for recognizing novelty. This dependence underscores the depth of the evidence. Quarks are not background assumptions. They are active components in every analysis. Remove them, and predictions collapse. The language of shadows may sound poetic, but in practice, it is technical. Shadows here mean statistical fingerprints, energy flows, and angular correlations measured with precision. Nothing vague remains. Over decades, physicists learned to trust these shadows because they never changed their shape. New detectors, new energies, new environments, all reproduced the same signatures. Repetition built certainty. This way of seeing required patience. It required letting go of the expectation that fundamental objects must be isolated. Quarks demanded a different standard of proof. That standard is now routine. Modern analyses assume quarks as given, not because they are seen, but because their effects are unavoidable. They shape every collision. Whether quarks have ever been seen depends on how observation is defined in particle physics. In this field, observation means constraining behavior through measurement until no alternative description remains consistent with the data. By that standard, quarks rank among the most firmly established entities in modern science. As detectors improve and datasets grow, indirect signatures become increasingly precise. Features once extracted statistically now appear as stable patterns across independent experiments, reproduced without changing the underlying method. When objects are known only through their effects, a further limit becomes unavoidable. Quarks are not accessed directly, but through how they shape energy flow, correlations, and structure in detectors. If that mode of discovery has proven sufficient here, it raises the possibility that other elements of nature may follow the same pattern present through influence rather than exposure, pointing beyond quarks without departing from the same experimental logic. Part 10. If the universe hides quarks, what else might it be hiding in plain sight? Here is a boundary that refuses to move no matter how powerful our instruments become, because quarks mark a limit where nature stops allowing separation and starts allowing only inference. At that boundary, the word fundamental begins to lose its familiar meaning. For decades, the Standard Model has described quarks as elementary. They have no measured size, no internal structure, and no subcomponents revealed by any experiment. Every scattering result, from SLAC to the Large Hadron Collider, is consistent with that description. Yet history encourages caution. Atoms were once considered indivisible. Protons and neutrons later held that status. Each time, deeper layers appeared when experimental reach expanded. Quarks sit at the current end of that sequence. The difference now is confinement. Atoms could be separated, nuclei could be split. Quarks cannot be isolated at all. The barrier is not technical, it is dynamical. This raises a serious possibility. Quarks may truly be elementary, or they may be effective descriptions of something deeper that cannot appear directly. Both options remain consistent with existing data. Physicists have explored this ambiguity carefully. Over the years, speculative models proposed preons, smaller constituents that might combine to form quarks and leptons. These ideas were motivated by pattern recognition rather than direct evidence. Preon models attempted to explain why quarks come in families, why charges appear quantized, and why symmetries repeat. They offered mathematical elegance, but experiments never confirmed them. High-energy collisions searched for deviations that would signal compositeness. None were found. Limits on quark size continued to shrink. So far, quarks behave as point-like entities down to distances far smaller than 1 atometer. At the same time, confinement complicates the question. If deeper constituents exist, confinement could hide them just as effectively as it hides quarks themselves. Absence of evidence remains ambiguous here. Quantum field theory adds another layer to this uncertainty. Fields, not particles, are the primary objects in the theory. Particles emerge as excitations of those fields. From this perspective, asking what quarks are made of may be misplaced. In QCD, quarks are excitations of a quark field interacting with a gluon field. The fields are fundamental in the sense that the theory requires nothing beneath them. Whether that sense matches physical reality remains an open matter. Richard Feynman addressed this tension directly. He once said, "I think I can safely say that nobody understands quantum mechanics." The statement was not resignation, it was precision about limits. In particle physics, prediction often outruns interpretation. Calculations work, detectors confirm them, understanding follows more slowly. Quarks exemplify this pattern. Confinement may be telling us something fundamental about nature's architecture. Some separations are allowed, others are forbidden. The rule appears absolute. This idea echoes beyond particle physics. In cosmology, dark matter reveals itself only through gravitational effects. Dark energy appears only through cosmic expansion. In each case, nature presents consequences without direct access to causes. NASA and ESA missions routinely work under these conditions. Observations of galaxy rotation curves, gravitational lensing, and cosmic background radiation infer unseen components with confidence. Direct detection remains elusive. Quarks fit this broader pattern. They are known through what they do, not through isolated observation. The universe appears comfortable with this arrangement. The Standard Model itself may not be final. It does not include gravity. It does not explain dark matter. It leaves many parameters unexplained. Yet within its domain, it works with remarkable accuracy. Attempts to go beyond it often preserve confinement-like behavior. String theory, for example, replaces particles with extended objects whose internal structure cannot be probed directly. Again, access is limited by principle rather than technology. Even loop quantum gravity suggests discreteness at scales beyond direct observation. The pattern repeats. Nature reveals effects before mechanisms. Quarks were an early example of this rule. From this angle, confinement looks less like a nuisance and more like a message. It marks where reduction stops and pattern recognition begins. Understanding proceeds by consequence. This does not diminish scientific rigor. On the contrary, it demands higher standards. Predictions must be precise. Models must survive repeated tests. Quark physics has met those demands for decades. Every jet event, every lattice calculation, every scattering experiment reinforces the same conclusion. Whatever lies beneath quarks, if anything does, it respects confinement. The rule holds universally. That universality is itself data. It suggests that limits are part of physical law, not gaps in knowledge. Some boundaries may be permanent. Carl Sagan often emphasized humility before nature. He wrote, "Somewhere, something incredible is waiting to be known." In the case of quarks, the incredible may be the boundary itself. The universe allows us to calculate, predict, and build technologies based on quark behavior. It does not allow us to pull one free and examine it alone. That asymmetry defines the relationship. Whether future theories will reframe quarks as emergent objects or confirm them as final constituents remains uncertain. What is certain is how discovery will proceed. It will proceed through indirect signatures, consistency across scales, and patience. The same path that led to quarks will guide what comes next. In that sense, quarks are not just building blocks, they are signposts. They show how far separation can go and where inference must take over. They define a style of knowing. As this series comes to rest, the picture that remains is not one of hidden failure, but of structured limitation. Nature offers patterns, laws, and consequences in abundance. It withholds isolation. That balance has carried physics from atoms to quarks and beyond. It continues to guide exploration today. Nothing suggests it will change. If you have followed this journey from confinement to evidence, from freedom to limits, you have already practiced the method science requires at its deepest levels. Attention to detail, trust in patterns, and patience with boundaries. As the night continues and the world grows quieter, these ideas can settle without urgency. The universe is not asking to be solved all at once. It reveals what it will, when it will. Thank you for spending this time exploring the smallest known structures of matter. Wherever you are listening from, and whatever pace the evening has taken, may the rest of your night be calm and steady. Sleep well, and let the universe continue its work.